the next step, moving down our list, is to go to water use and demand management and water supply and infrastructure. So we'll cover that first in, let's describe what that is first. These are the two other components we want to cover. The first one is water use and demand management, and those are the following four components that Vicky described earlier this morning, and that's potable uses, drinking water, non-potable uses, including outdoor water, potable demand management, which is one of the management actions that we have that will affect the demand, both potable and or non-potable, and then septic is also within the group of options. Going back to our schematic diagram, these are the components that we will be managing. So what I will do now is, with the magic of television, just switch back to a demo data set where we've populated information that we're interested in for this case study. So we've provided this data set on the CD as well, and that's the demo data. So the first component is the potable demand. So as the term implies, this is demand for water that's been treated to drinking water standards. What WMOST needs is a time series of total demand for each of our users. The initial setup will reserve some space for unaccounted for water that's always present, but in setting up the WMOST, you would specify how many users you want to have. In this case, we had in the blank WMOST specified 4 users, and then in the blue space at the top, you would type in, the labels you want to provide to these users, and those labels are carried forward in all of the tabs that deal with demand. For each of these users, what you will then need to provide is a time series of the demand. The time series would come from utilities data in Massachusetts. It could also be from the ASRs, the annual statistical reports that the utilities provide. And what we typically would want to do is develop that time series sort of offline in a blank Excel workbook, and then copy and paste, as simple as that, into the WMOST blue space that's been provided. The other information that is contained on this tab is the average percent consumptive use, and that will be specified by month, even if we have a daily model. And anyone can tell me why this would vary by month over the course of a year? We're talking about the percent of total demand that's consumptive.
Watering lawns.
Bingo, watering lawns. So you see on the table that the consumptive demand during the summer months peaks, and that's the reason. Are you specifying spatially where these are? No. This is going back. This is a launch model, so it's one system.
That's like 1, 2, 3, 5 columns specified. No, can you add columns?
Yeah, in the setup, if I want to go back in time, and in the blank setup, if say I said I have 6 water users, it would have created 6 columns. You would still have unaccounted for water, and then you'd have 6 columns next to it. So the next item, we've done that. The next item would be non-potable demand, and this includes outdoor watering. What you want to specify in this tab is the maximum potential, so the maximum potential non-potable water use. That's out of the total demand. And then the average percent consumptive non-potable water use. Let me go back to the notes. And these, so this is basically, here what we're doing is we're defining the percent of the demand that could be met by non-potable water. So it could be toilet flushing, for example, and that will allow the model to know how much of the total demand it can meet by not going through total drinking water treatment plant. So that's the purpose of this particular setup. And the values you see in here are default values we've used in a number of different studies. The third tab gets to management actions that can affect the demand in the model. There are 2 ways to affect demand in WMOST. One is through a price signal, and what we're doing in the first tab would be to specify the change in demand for a percent reduction in demand per percent increase in price. The values for this would typically come from the literature or for a study that may have been done by the utility. We're turning this off in this model because what we're interested in is a given demand, how do we meet that demand and minimize impacts or minimize impacts on flows. So we don't want to turn this on, but this would be the place where you would enter the initial cost of that water service fee increase. That could be a cost of a study, for example, O&M cost. And then the maximum price change that you're enabling in the model. Say, I don't want to increase price by more than 20%. This would be specified as well. The second way to affect demand is by providing a rebate, say, to your water consumers or your households, and have fixtures that save water. So you could have a program where you have low flow toilets, and that will give you a certain demand reduction that is not necessarily based on the rate of the water. So you would enter this information here. Again, for the purpose of this particular case study, this is not a relevant management action. And then for septic, we would specify the number of consumers within our area, our study area, that are served by septic systems and that recharge inside our study area. And so this would be the water that basically returns after it has gone through each household or each consumption point, and that would return to the aquifer within our watershed. We put the percentage here, and then the percent of similarly public water served consumers that are on septic but that recharge outside of the basin. So there might be the utility that we're modeling might also deliver water to consumers that are outside of the spatial area, and we want to capture that appropriately in our model. So that'd be a good place to do that. So those are the 4 components related to water use in our model. So we've basically gone through item 3. The 4th step builds our water supply and infrastructure. And there are two major components. One is surface water, one is groundwater. Within surface water, we have our stream channel and the reservoir, which is at the bottom of our watershed. And these are the components we're referring to and that we'll see through the model. So we have our three, and then we also have the external, private, and sort of non-utility withdrawals and discharges, both to surface water at the top and then to groundwater at the bottom. And we'll see how those get entered into WMOST. So the first one that we come to is the surface storage. So for surface water, we have the main channel, and we also have a reservoir surface storage that's defined at the bottom of the watershed. The set of entry cells at the top define our surface storage. And there you have the initial reservoir volume, minimum target reservoir, minimum and existing maximum. And existing maximum is the sort of the would be determined by the maximum stage that you can reach in the reservoir. We also here specify the construction cost and O&M cost. And like other management options, we can either turn this on, which would enable the model to add capacity to our reservoir so we can build additional volume within that reservoir to meet the demand over time, or turn it off. So in this case, it's turned off. The series of time series, the time series at the bottom basically give you the withdrawals or discharges to the surface water. So Vicky covered some of examples before, but for other surface water withdrawals, those could be industrial users who are withdrawing from the same surface water main channel that we want to account properly in the model, because we're typically focused on the utility. You may also have, similarly, they may discharge to the surface water. So if you have those discharges, then they get entered as a time series. And similar to what I described for the demand, you would build that time series and then copy and paste it. The watershed may not be at the headwater of a basin or that you're modeling, so there might be actually inflows coming into your main channel, and those need to be added to get a accurate representation of the flow in your main channel. So you would do that here. And the last three columns basically give you a similar setup, but for the reservoir.
So the withdrawal from reservoir, is that still reservoir?
So, for example, if you have a drinking water reservoir, yeah, you might have another town that withdraws from that reservoir to meet their demand, and you want that to be reflected, because what you're going to be modeling is what this utility's effect on the reservoir is, but there's also separate withdrawals that would not be accounted for in the system unless you add them separately.
There's no reservoir spill in the
yeah, there's an outflow when it gets that. So this basically gives us our target minimum or maximum stream flows if we want to specify an objective where we must we must manage our system to meet this minimum inflow. You could have, for example, a minimum inflow of 0.5 cubic feet per second in June as the minimum you must meet in your solution. As in this case, what we've specified is on the reservoir, and that's the minimum outflow from the reservoir in July, August, and September. Because our reservoir is at the bottom of our watershed, this in fact is the minimum outflow from that reservoir outside the watershed.
So those other, the minus 9s are basically null. Like
Yeah.
Why is it negative 9.0 in those, or doesn't that matter?
It just basically turns it off. This means that for...
But negative, right, but before it was negative 9 and here it's negative 9.0.
It's just a display. Yeah, it's just a display. But what this means is for January through June, I really don't care what the flow will be. In July, August, September, I need to meet these minimum outflows. And then the rest of the October through December again. Yeah, they're specified in the case. What do you mean by safe yield?
Well, I mean, it's the minimum threshold.
Yeah, it's the minimum that's needed in the reservoir outlet. So the second component that we have to specify is groundwater. And just like the reservoir, basically it's a stock, so we need to specify an initial volume, a minimum volume, maximum volume. We also, here's where the groundwater recession coefficient gets defined, and that defines the relationship between groundwater and surface water in our model. That gets populated when you use the assisted setup, it gets populated from that HS model. But that is one of the parameters that we can play with if we notice that the fits between the measured values and the model values are not that great in the case of calibration and validation. We'll come back to that this afternoon. Similarly to what we had for surface water, we have to define...
The initial groundwater volume, that would be the groundwater volume for the start of the simulation period.
Correct, yeah. So on January 1st, 2004, we need to have at least this amount of water. And you can back calculate that value. It doesn't have a huge impact on the simulation as long as it's large enough that you don't run out of water before before you can sort of refill and get steady state. To back calculate
the initial groundwater volume.
You can back calculate it based on the flow. I usually just make it large enough. So other groundwater withdrawals might be if you have people who have private wells within the watershed, they're not served by the public system, you would want to enter those as other groundwater withdrawals so that your groundwater is appropriately represented. Groundwater discharge, that could be injection wells, it could be septic systems from other towns that are not, again, represented by the infrastructure within your watershed, but that add water to your groundwater stock. And then this is not as frequent. There's a possibility of putting an external groundwater inflow where there's a mismatch between the spatial extent of the area that you're modeling and the aquifer. And as we have for surface water, you can define your scenario so that you achieve a minimal external groundwater outflow. If that's the objective you're trying to meet, then that would be where you would specify it. In our case, we want to basically have water in the aquifer at all steps, so that's set to 0 as a minimum. The next piece component of our sort of built up is this interbasin transfer, and that is meant to represent exchanges between this watershed and external to the watershed as far as water coming into to meet the demand or leaving to handle the wastewater. So you would specify the cost of implementing this management option, and for example, it could be the cost of a connection to MWRA as a supply of water. And so there's a upfront cost, and which is specified here, and there's also a purchase cost on an ongoing basis. You're going to have to pay X number of dollars per million gallons. For our model, we have a wastewater treatment plant. There's a cost specified for basically managing the quantity of water of $1,000 per million gallons. There might be existing limits on the amount of water that can be brought into the system or that can leave the system, and you would specify it there. For our case study, the water, there's basically no IBP for existing water, so that's set to 0. And then you can add additional capacity and specify how much additional capacity you will enable in the model. So all of these tabs sort of share a common setup where you specify the dimensions that exist, you specify costs, and those costs are capital costs and O&M costs, and you also either enable or turn off management options. The last tab builds our water supply infrastructure, and there's a couple of assumptions up front that specify the planning horizon, and that will influence or determine the annualization period, especially for new infrastructure. You also would specify your interest rate. That would be the discount rate that's applied to a capital expenditure that in effect annualizes it to a recurring charge each year. And then sort of working through the list, we have the price for water. So this is the consumer price for, potable water. That specifies the fixed fee and variable fee. That is used to calculate for a given amount of water delivered in your system, how much, what's going to be your revenue as a utility. Groundwater pumping, pumping costs, existing capacity. Also, you can add capacity, so this would be, again, where you would specify the cost of adding additional pumping. Same for surface pumping. So a lot of those types of cells sort of repeat. And here on the right, you see that the exclude new additional is actually blank. This, by leaving this blank, it enables that particular option to be selected, and that option being the option to build additional capacity for groundwater pumping. So right now we have 1.3 MGD of pumping capacity for groundwater. We're telling WMOST if it needs more capacity at the cost that's been specified, it will build it and will deliver the amount of water accounting for the additional O&M costs that go along with that volume of water that's now being incrementally delivered. Same for surface water pumping, water treatment plants. There's a cost for adding capacity for drinking potable water treatment. Another option is to fix leaks. that is also enabled in the system. We get to wastewater treatment, similarly cost to add capacity, cost to operate, cost to fix leaks, water reuse facility. So all of these are the various components that you see on the diagram that are the sort of human or engineered infrastructure. The last one is the oddball in the on this tab, and that's something called makeup water. That's more of a virtual infrastructure option. It basically enables the WMOST to create water if it needs it. And we'll get into that during the discussion and validation and calibration this afternoon, but it's a safety valve for WMOST to use if it, during the simulation or during the optimization, it finds that it just cannot meet that demand given the option that you've made available to add pumping, to put additional capacity in your reservoir. It will go fetch that amount of water, make it up, and attribute this very high cost. So it's very a last-ditch option that it has available.
Where did all the costs come from?
Was there a question?
Yeah, where did all the costs come from?
So some of the costs, like the utility rates for water, those would come from the utility itself. Operational costs like O&M, pumping, water treatment costs would come from the utility. So we've obtained a lot of those costs for the various case studies that we've done from the annual report by the utility. So we might look at electricity prices, prices of chemicals used in treating water. So that's the source of those costs. So that would vary from location to location.
Stormwater utilities fit in here?
There's a question about stormwater utilities and would they fit in there.
Stormwater utilities?
Fees that residents or businesses are charged.
Fees that are collected by stormwater utilities for management of stormwater.
I don't know that that's accounted for. Sorry, I'm thinking out loud. Where would you count for that? Does that get attached to the wastewater treatment plant? It would depend on how they build that into their pricing structure.
At the municipal level, not necessarily.
Yeah, there's a comment that might be collected at the municipal level, not the utility.
Right, and I sort of wonder whether it would be in a fixed fee for each connection, but I think it depends on how they account for it. Any other question on the infrastructure tab?